Okay, so we start our presentation for the introduction. The development of 5G infrastructure technology has promises an important revolution, especially in mobile communications. The revolutions include transforming connectivity, communication, and engagement. It also provides extremely high speeds and low latency, and then it supports critical communications, industrial automation, and IoT. Then the critical role of materials in 5G infrastructure. It is important to use proper materials in order to have performance enhancements, thermal management, and also reliability and efficiency for the 5G. So the key component in 5G infrastructure is semiconductor, which we focus on this assignment. It is because semiconductor is crucial for signal processing, data transmission, and power management. And also traditional silicon, which is previously used in 4G and 3G, has reached its performance limits. So it is a need for an advanced material to be used in 5G infrastructure. So materials that have been chosen is gallium nitride and also silicon germanium. Gallium nitride, the first material that have been chosen, is a composition of gallium and nitrogen. Uh, Gallium nitride is very ideal for high frequency and high power applications, just like 5G infrastructure. It is being chosen because of its capabilities of handling higher frequencies, greater voltage, and also have a better thermal management. So the next material used in the 5G infrastructure is silicon germanium, which is combines advantages of silicon and germanium. It has an exceptional electron mobility and compatibility with silicon-based production. The applications of silicon germanium can be used at high frequency and mixed signal integrated circuits, especially in 5G.
Okay, thank you to Faris. So now my name is Muhammad Shazwan Sarudin, and I will present about the physical properties of the gallium nitride and silicon germanium. Okay, so gallium nitride is crucial for advancing 5G technology due to its exceptional properties, such as supporting high power, high frequency, and robust thermal management. Okay, so its suitability for demanding 5G infrastructure like power amplifiers in base station, as it can handle significant power levels required for long distance signal transmission. So first of all is the ability for wide bandgap energy. The wide bandgap energy, which is around 3.4 electrovolt, enables operation at higher voltages and temperatures compared to traditional silicon. So it is crucial for 5G application involving high power transmission. With a high breakdown voltage, which is around 3.3 megavolt per centimeter, the device can manage high power levels reliably, enhancing the efficiency and reliability of 5G base stations. Its electron mobility uh, enables high mobility enables rapid signal processing, essential for high frequency applications like 5G networks with high data rates and low latency requirements. Also, its high electron saturation velocity, which is around 2.5 mega centimeter per second, supports fast switching speeds in transistors and electronic components, ideal for the millimeter wave frequencies used in 5G communications. Okay, next is a high thermal conductivity. Its high thermal conductivity, which is around 130 to 230 watt per meter Kelvin, enables effective heat dissipation crucial for maintaining device performance and reliability in high power application. So its ability to withstand temperatures up to approximately 400 degrees Celsius ensures resilience in harsh thermal environments, typical in outdoor 5G installations. For the microscopic character, gallium nitride also possesses a unique microscopic characteristic crucial for its role in 5G technology, which is it has a typical woodside crystal structure, enhanced electronic properties, especially in high electron mobility transistor. Also, it inherent polarization effects resulting from its asymmetrical structure amplify electron density at GaN substrate interface, essential for high-speed transistor operation, thus enabling rapid signal processing in 5G networks. Additionally, advancement in epitaxial growth techniques refine its microscopic features, minimizing defects and dislocations, consequently enhancing material quality and device reliability. So next is the silicon germanium. The silicon germanium, first is it has a variable bandgap energy. Its bandgap energy varies to 0.66 to 1.12 electrovolt based on germanium content, making it adaptable for specific applications. This tunability enhanced performance in high frequency and mixed signal integrated circuits valuable in 5G technology. So it also boasts high electron mobility to up to 2000 centimeter square per velocity second, based on germanium concentration, enabling swift electron transport vital for high-speed data processing and communication in 5G networks. Its superior mobility compared to pure silicon makes it deal for speed critical application. So next is for the breakdown voltage. It's actually germanium silicon actually has a breakdown voltage lower than gallium nitride, but it exceeds that of pure silicon. While not as critical as in power amplifiers, the reliability at high frequencies remain essential. It's because its dielectric constant, which is around 11.9, affects the device capacitance and impedance, improving RF circuit performance through better impedance matching and signal integrity. Next, it's the thermal conductivity. Uh, Silicon germanium thermal conductivity is around 60 watt per meter Kelvin, which is lower than gallium nitride, but adequate for many high frequency applications. Effective thermal management techniques maintain performance in high speed operations, and also its expansion coefficient aligns with silicon, ensuring compatibility and reducing thermal stress in silicon based integration. The silicon germanium also boasts unique microscopic characteristic, which is ideal for diverse application in 5G technology, which is as an alloy of silicon and germanium. It offers adjustable electronic properties based on germanium concentration, enabling tailored performance. Its notable characteristic lies in strain engineering, varying germanium content induces strain in the crystal lattice, enhancing carrier mobility, crucial for high-speed transistor operation in 5G circuits. This enhancement accelerates electron transport, facilitating rapid data processing, vital for efficient 5G communication. So that's all from me. Uh, Next is my team member. Thank you.
Next, I'm going to continue on the mechanical properties of both gallium nitride, GaN, and also silicon germanium. So as for gallium nitride, due to its excellent mechanical and electronic properties, it has been an ideal candidate for 5G application. GaN is also widely used in optoelectronics and photonics due to its wide bandgap and excellent material properties. GaN is a rigid material with high values of hardness, typically about 12 to 14 gigapascal as per the Vickers scale. Such an excellent mechanical property in hardness is necessary for durability and application under high frequency and power levels. Furthermore, GaN has Young's modulus of roughly 300 to 350 gigapascal, which is very stiff against deformation under loading and crucial in the maintenance of a structure. Despite being at the distant end of the scale for hardness, GaN is relatively brittle compared to other microstructural materials, having low fracture toughness of 1.5 to 2.5 MPa and power of 0.5. However, being compensated with very high thermal conductivity, which is essential for getting rid of vast amount of excess heat developed due to the high power effect, aiding the device in not getting destroyed due to overheating, so it can perform adequately within its working environment. GaN's high thermal stability and piezoelectric constants make it suitable for various applications. In its microstructure, GaN presents a hexagonal wazite crystal structure, granting a more robustness and dense atomic packing. The nanoporous properties of GaN has emerged as a promising material for optical and optoelectronic device. Although the electronic and mechanical properties of GaN can be adversely affected by common structural defects, such as threading dislocation and point defects, these have been significantly reduced through advancement in material processing techniques, which enhance overall performance. GaN nanowires show potential for high power transistors, and light emitting device due to their one-dimensional structure and physical properties. Reduction of grain boundaries in GaN is also an incremental factor to consider, since the existence of grain boundaries affects electromobility and mechanical strength. The existence of these grain boundaries in high quality GaN aims at minimizing them to realize better performance. As for the silicon germanium, the silicon germanium alloys have been widely accepted in radio frequency application because they exhibit good electronic properties and are compatible with silicon technology. This makes them hard enough, around 7 to 9 gigapascal, to integrate electronic devices without damage, yet remain slightly flexible. Young's moduli values for silicon germanium are around 130 to 150 gigapascal, which means some sort of compromise in rigidity has been obtained while retaining mechanical integrity. The coefficient of thermal expansion in silicon germanium is lower than that of silicon, thus reducing the thermal mismatch and mechanical stress in assemblies. However, its thermal conductivity of between 20 to 60 watt per meter Kelvin is modest compared to GaN, but it is still adequate for radio frequency application. Silicon germanium has a similar crystal structure to silicon, the cubic diamond structure. The lattice strain resulting from adding germanium enhance electronic properties. However, it becomes challenging to manage point defects, such as misfit dislocation because of a lattice mismatch between silicon and germanium. These defects can be controlled by the precise control of the germanium content and epitaxial growth conditions. Advanced epitaxial techniques leading to the buildup of single crystal silicon germanium layers minimize grain boundaries on these layers, resulting in improved mechanical and electronic properties.
Assalamualaikum, my name is Muhammad Amar and I will discuss about the fabrication method and the application of this material. The material that we choose is gallium nitride and silicon germanide. There are a few fabrication methods of gallium nitride and silicon germanide, and I will focus on the chemical vapor depositioning that is commonly used in semiconductor industry. Okay, what is chemical vapor depositioning? Chemical vapor depositioning is the method used to depositioning a solid material from a vapor by the chemical reaction. This process involves the chemical reaction of gaseous precursor that will decompose on the substrate surface to form the desired deposit. For gallium nitride, the commonly CVD deposition used is metal organic chemical
vapor depositioning, or MOCVD. The anneal substrate placed in the reactor chamber heated around 1000 degrees Celsius until 1100 degrees Celsius. The metal organic precursor and reactant gases are introduced to the reaction chamber, and the atmospheric pressure. At this elevated temperature, the metal organic compound decompose, and the metal atom react with the reactant gases to form the thin film on the substrate surface. This is the diagram for the chemical vapor depositioning. For the silicon germanite fabrication method is same as a gallium nitride, which is chemical vapor depositioning, but it happen at low pressure, which is below atmospheric pressure. Okay, next, the application of the material itself, which is gallium nitride and silicon germanite. These two materials is widely used in semiconductor component. Semiconductor industry will choose this material because of the characteristic and the advantages of this material. First semiconductor that I will explain about the transistor. Transistor function is to process the tasks like encoding, filtering, and decoding signal. With gallium nitride and silicon germanide, the process take a shortened time compared to traditional material. Also, transistor is providing superior power amplification and thermal management for better performance. Transistor also handle the complex signal process task. Material characteristic itself can help the signal processing in the component. Next, the application in the integrated circuit or ICS. What the function of IC? The function is amplify the signal. It's boosting signal over long distance and improving communication. With the gallium nitride and silicon germanide, it can handle higher frequency and power level than better than traditional silicon.
And lastly, for the conclusion, the advancement of 5G technology critically depends on material used in the infrastructure. Critical enabling materials include gallium nitride and silicon germanium. GaN has a very high thermal conductivity, high power density, and superb electromobility, which are critical for the high frequency, high power requirements of 5G networks. By its capability to operate at higher voltage and temperature requirements, GaN assures robust performance and reliability. Furthermore, the superior thermal management realized by GaN helps to maintain efficiency and device longevity, which is vital for continuous and high-speed data transmission as demanded by 5G technology. In contrast, silicon germanium offers substantial advantages through compatibility with current silicon-based manufacturing processes, making it an economical solution for integrating novel functionalities for 5G application into existing infrastructures. The tunable electronic properties of silicon germanium are due to its variable silicon to germanium ratio, and it allows performance level for high frequency and mixed signal application to be optimized. This property is a considerable importance since 5G will have many needs, such as radio frequency, components, and more complex signal processing units in a single integrated circuit. It is with both GaN and silicon germanium together that the crucially emerging challenges of 5G technology in higher data rates, low latency, and better connectivity will be addressed. The high electron mobility and thermal stability of GaN sustain efficient high power amplification. In contrast, the electron mobility enhancement and compatibility with silicon technologies of silicon germanium enable more rapid signal processing and integration. The combination of such material allows for developing high-performance radio frequency amplifiers and integrated circuitry that are crucial for ensuring the reliability and efficiency of 5G service. In conclusion, integrating GaN and silicon germanium materials into 5G infrastructure significantly improves the performance and reliability of the network. Using these materials provides properties for supporting high-speed, low-latency communication that guarantees 5G technology meets increasing demands for modern communication system. With further evolution of 5G, GaN and silicon germanium are set to provide the critical enabling technologies for technological strides toward the future of mobile communications. That's all from us. Thank you.